Good morning. This is Yunfei from Skek USC. Today, I'm going to show how the fault geometry controls the 2015 Nepal Gorkha earthquake and its near-field ground motion. 2015 Gorkha earthquake is magnitude 7.8 and occurs in the continental collision belt between the Eurasian plate and Indo-Australia plate. Historically, there were multiple big earthquakes in this region, a magnitude 8.5 in 1505 in the west and a magnitude 8.2 in 1934 in the east. The Gorkha earthquake overlays on the south region of a magnitude 7.6 in 1833. From its focal mechanism, it is a shallow thrust event, implying the fault plane is almost flat, about 6 degrees of deep angle. A very noticeable feature about this earthquake is that its ground motions have very prominent impulsive signals. There were three stations recording the horizontal and vertical ground velocities. Kicking 4 is on the bedrock, and the rest of two stations are on the Kathmandu Basin. In the horizontal component, there are source-related impulsive signals and basin-related oscillations. More apparently, in the vertical component, there are impulsive signals with very similar dominant periods. What does the impulsive signal mean for engineering applications, aka buildings? As shown in the left figure, that during this earthquake, the observed ground motions at the period from 4 to 6 seconds is higher than the ground motion prediction, three different models that were used for construction design. In other words, this earthquake has unexpected high ground motion in the long period band that is very sensitive to the safety of higher rise structures. Here's one example. It is called Darahara Tower, a nine-story historical monument. It was completely destructed during the earthquakes. But look at the surrounding smaller buildings, they were almost intact. That is because the ground motion in the short period is not sufficiently strong to destroy them. Actually, this feature is not very special. The pulse-like ground motions are very, very pervasive. It is found in Chichi, San Fernando, Northridge, Landers, earthquake, and so on. Besides, this signal is very dangerous. Look at the record of the largest recorded value of the horizontal PGV over time. This curve is almost updated by the pulse-like ground motions in Parkfield, San Fernando, Tabas, Northridge, and Chichi. So we have to ask what's the reason of Gork earthquake contains the pulse-like ground motions, so that it generates the pulse amplification in ground motions. Actually, there are multiple candidates. It can be related with the pulse-like rupture, source effect. The pulse-like rupture could result from the rate-dependent friction, fault geometry, heterogeneity, a low velocity fault zone, or the rupture directivity could be also another reason. For example, the pulse is seen in the forward direction, such as the Lucin Valley station of the Landers earthquake. In this study, our hypothesis is the pulse-like rupture caused by the 3D complex fault geometry. In this study, we adopt geologically plausible fault geometry. It is oval-shaped. In the middle, the fault consists of 5 segments: flat, dip, and flat. The flat portion has a dip angle about 6 degrees. In contrast, in the east and the west, the fault becomes three-segmented: flat, dip, flat, dip, and flat. The lines here are the depth contour of the fault geometry. Moreover, the oval-shaped flat portion of fault geometry is consistent with the coseismic slip distribution. To enable the spontaneous rupture on the fault, we implement rate-intensity friction on the fault and apply velocity weakening on the flat portion, and the rest area is velocity strengthening. The upper and the lower limit of the velocity weakening segment are adjusted to accommodate a consistent seismic moment with observation. We apply homogeneous stress tensor and the shear and normal traction are perturbated due to the irregular fault plane. Besides, we also implement homogeneous rock materials, plasticity parameters. In summary, the only complexity in this model setup is the fault geometry. Here are our simulation results and comparison with kinematic studies. This is our preferred model that has a similar sleep distribution and a peak and average sleep value with kinematic studies using near field GPS and INSAR data. The simulated rupture velocity is saturated along the strike distance at around 90% shear wave speed. This is the mode 3 dominant rupture. As you know, the theoretical terminal rupture velocity for this case is shear wave speed instead of the relay wave speed. In this study, the plasticity we applied helps to saturate rupture velocity to observationally consistent value from the back projection study. This comparison shows that the simulated rupture also has a pulse-like characteristic. It bounded by the upper and the lower limits of velocity weakening area or the along dip extent of rupture area. Besides, the depth-dependent radiation pattern found by the kinematic study is also reproduced in our simulation. In the observational studies, the deeper part or down dip is high frequency dominant. On the contrary, the shallow up dip is low frequency dominant with bigger rise time and a simpler pulse. This pattern is also seen in our simulation that the rupture on the shallow flat portion has a larger rise time bounded by the rupture extent, and the rupture on the down dip here is controlled by the much smaller down dip asperity, thus resulting in a very high frequency radiation. Because Gorkha earthquake is only 15 kilometers deep and the seismic waves excited by the large amount of sleep will be reflected back from the surface and impact the rupture on the fault. I compared the whole space and half space model to investigate the free surface interaction, and showing this figure, the seismic waves will reduce the normal stress on the fault and amplify and broaden the slippery function. We compared the rise time of slippery function of half space and half space models and find that the half space model have overall longer rise time. More specifically, we find that there are two peaks in the rise time distribution that correspond to the down dip and up dip segments. In this figure, it shows that the rise time peak on the down dip with much larger dipping angle shows insensitivity to the free surface. On the contrary, on the flat dipping and flat up dip portion, the peak rise time of half space model shifted right to a larger value by about 2 seconds. The difference is 2 seconds. Hence, the free surface effect are important to shape the rupture in a shallow thrust earthquake. As we described, the Gorkha earthquake is essentially shaped by the along dip rupture extent and the free surface. Then we modify the rupture extent along the dip by adjusting the upper and lower limits of velocity awakening portion. It could only cover the flat segment or a little extrusion to the shallower or deeper segments with higher dipping angle. Very luckily, we have the one bedrock high rate GPS station right above the rupture. We use this record of vertical velocity to constrain the along dip rupture extent. The red dashed curve corresponds to the case that the upper and the lower limits are nearly at the rim of a flat portion as our preferred model. If we move the upper limit upward to 987 kilometers deep, allowing the rupture on the shallow dipping segment, then the simulated velocity shows broader pulse, but with a second peak, due to the change in the radiation pattern, which is not seen in the data. The green one is data. On the other direction, if we extend the lower limit from this rim to deeper part, then a bigger and a broader, the green one, the bigger and the broader pulse will be generated. It is noted that in this comparison, we didn't filter the data, and the simulation and the data can be accurate up to 2.5 hertz. Given the near field high rate GPS, we confirm that the rupture is nearly bounded by the upper and lower limit of the flat portion. The characteristic period of the near field ground motion is also attributed to the oval shaped flat portion. Let's revisit our methodology. In this study, the freedom we can choose from our model includes the rupture extent, stress drop, of-fault plasticity. The constraints that are either inherently included in our model or fit by tuning our model includes free surface, fault geometry, seismic moment, rupture velocity, and the most importantly, unfiltered GPS record. Overall, through this validation, it is indicated that the 3D complex fault geometry is the first-order dominant factor controlling the 2015 Gorkha earthquake, and it is confirmed by a near-field ground motion record. Okay, take-home message and paper. This study has been published in the JGR Solid Earth. Our dynamic rupture model based on the geological possible fault can reproduce the earthquake parameters inferred by the kinematic studies. And this is the first dynamic rupture model of Gorkha earthquake, which addresses the interaction between the fault and the reflected waves, which fits a near field ground motion. And the 3D fault geometry inferred from the geological study is the first order dominant factor in 2015 Nippon earthquake. That is also confirmed by a good unfiltered fitting with near field GPS recording. Thank you.